Okay, it is hot as hell here, but can't be outside anyway, so I'm recording some podcast. Continuing with this book on demystifying climate models, let's look at the atmospheric component of the my computer here is really insisting on giving me trouble. Okay, so let's look at the atmosphere and its role in the climate system and what some of the modeling issues are very briefly. Emissions and evaporation from the surface. Okay, this is funny here. As well as radiation force the atmosphere from below. The sun forces the atmosphere from above. Chemistry, clouds and winds occur in the atmosphere along with flows of radiation. So atmosphere in that sense is very different from the ocean. Atmosphere is largely forced from the bottom in addition to some of the radiation and heating that occurs within the atmosphere. So if you look at the broad schematic of the structure, of course it has interactions with the ocean and land, and there is human activities forcing it as well. So like as you would expect from the friction at the surface, which I said before is lower on the ocean, because as the winds blow over the ocean, ocean can move and reduce the friction, whereas land is solid, so the friction is higher, and on land it depends on vegetation, desert, urbanization, and so on and so forth. So basically you end up with a boundary layer. Boundary layer physics is a very complicated business, and there are people who spend a lifetime just working on modeling the boundary layer, and you can have clouds within the boundary layer, and then we have what is called free troposphere, which has the strongest winds, because within the boundary layer friction obviously affects the winds. And you remember the basic structure of the atmosphere: warm near the surface, cooling to the top of the troposphere, what we call tropopause, and then temperatures warm again because of the ozone formation and trapping of the high energy UV radiation in the stratosphere. And there are lots of issues about how the waves propagate up and the interactions between the stratosphere and the troposphere, but troposphere is where most of the action happens, so it's forcing from the top and forcing from below. So some small percentage of the short wave that's coming in is absorbed in the atmosphere. A lot is reflected by the clouds and from the surfaces, and the ocean absorbs some, and there are places where land can absorb, especially when there is water, soil moisture, and so on. But it is the outgoing long wave radiation that's going to largely force the atmosphere, as well as the condensational heating, especially in the tropics, when expanding air condenses and creates a lot of rain, especially in the ITCZ, the Western Pacific monsoon regions, and so on. And there are chemistry. Ozone is oxygen splitting and forming ozone is the big chemistry in the stratosphere, and troposphere has many more detailed chemistry happening. A large part of it is, of course, humidity interacting with cloud condensation nuclei, forming clouds, aerosols, carbon monoxide, carbon dioxide, OH radicals, and so on and so forth, and some ozone formation as well because of the pollution, which is not good for health or the crops and so on. So these are kind of generally the processes, and then on land you have to worry about hydrology and precipitation and evaporation, similar to the ocean, flow of waters, mountain glaciers, land ice albedo feedbacks, cloud feedbacks, and so on and so forth. So the energy budget then becomes very critical. Solar energy or shortwave radiation in yellow comes in from the sun. Energy is then reflected by the surface or the clouds, or it is absorbed by the atmosphere or surface. Most of it, of course, is absorbed at the surface. Surface exchange includes sensible heat, which is is just due to the temperature difference, so that's shown here as a small part of it. And latent heat associated with water evaporation and condensation, as shown here, associated with the cloud processes. Terrestrial infrared long wave radiation, shown in purple here, emitted from the Earth's surface, is absorbed by the atmosphere and clouds, which is what the major part of the greenhouse effect is, and that's what is giving us climate change in terms of our impact on changing the transparency of the atmosphere to outgoing long wave radiations. Some escapes to space, outgoing terrestrial radiation, and some is re-emitted back to the surface by clouds and greenhouse gases. We have done energy balance calculations elsewhere, but this is just to remind ourselves that incoming short wave, some of it is absorbed, some of it is reflected by clouds, a lot of it makes to the surface. Surface albedo reflects some, net albedo is 30% for the Earth, changing of course with climate change a little bit. Outgoing long wave radiation has to balance this, but if you increase greenhouse gases, then they're going to trap more energy and send it back to the surface. This bouncing around warms the surface and the atmosphere. Then there is an imbalance in the outgoing long wave radiation, and atmosphere moves that heat as well as the ocean, which takes up 93% of the excess energy that is trapped by increased greenhouse gases from human activity. Just as we saw before for the climate models, there are a hierarchy of models in the for the atmosphere as well. Different types of atmospheric models. Here is the box model or zero-dimensional model that we talked about, or it could be averaged spherical model like this, or 0 dimensions. Single column model, 1 dimension in the vertical, let's say, with exchanges happening, fluxes, let's say with the next column, and vertical exchanges. Many process studies are done this way, and there are some very good insights gained from doing this, which makes life simpler rather than running a full model. Then you have two-dimensional models. You can have an ocean surface, land surface, and the atmosphere has two boxes that's receiving energy, exchanging matter like air and water vapor, for example, and so on. And multiple column models of intermediate complexity. So complexity is kind of not a very well-defined term, but it's basically the number of processes you include and the number of processes you represent by simplifying in some form or the other. So multiple column models, sometimes multiple column models, are intermediate complexity models with columns representing a region like a country. So they are basically two-dimensional, 1 dimension in space and 1 dimension in height. So that's, you can see again horizontal exchanges and vertical exchanges here. Limited area or regional model, these are very common when you want to do a high resolution regional weather and climate, because you can then have lots of resolution and prescribe the boundary conditions from somewhere, like a global model or a reanalysis product, which basically is a blended model data product, which is a reconstruction of the past, a dynamically interpolated past weather and climate data. And this is the global grid general circulation model, which has basically got the entire equation system. If it's an atmosphere only model, then obviously the ocean is prescribed as sea surface temperatures. Often land has some interaction because it's a fast time scale interaction with soil moisture and other processes represented. So hydrology is represented in some form. The general circulation of the atmosphere basically refers to the cells that we have talked about elsewhere. So the Hadley cell, the polar cell, mid-latitude eddy dynamics, depending on what the resolution is in the horizontal, and vertical resolution determines how well the stratosphere troposphere interactions are represented, and so on. And you have basic features like the trade winds, mid-latitude westerlies, polar easterlies, and so on. So visible image of the Earth with the general circulation is overlaid, so you have in the background visible image from a satellite as the water vapor image in 5.4. So basically there are reasons why there are tilting structures, and there is the ITCZ in the low latitudes corresponding to the wet regions. So wet regions with rising motion around the equator in the upward branch of the Hadley cell. Trade winds blow westward in the tropics, so they are called easterlies. Downward motion in dry regions where you get deserts, and even the ocean has a desert with converging motion and basically no phytoplankton near the surface. Then it's wet again in the mid-latitude region, so the storm tracks with eastward winds or westerlies. Obviously, very brief introduction. Without equations, you're not going to get much more than that. So general circulation model then as a schematic of calculations in a time step in each grid box of a general circulation model, including the calculate where we calculate the processes. So for each point on a grid, you have a vertical column where vertical exchanges and horizontal exchanges and radiation out to space and receiving from the sun are happening, and some exchange happens at the surface with the ocean or land. And so calculating processes include clouds, precipitation, and so on, and radiation balance has to be done, and surface fluxes and top of the atmosphere fluxes are involved with all the non-linear advective mixing processes, convective processes, so various different time scales depending on at what latitude you are looking at. And there are equations to be solved for motions and exchange between the boxes. Okay, so obviously once you have such a model, as we said before, it can be coupled to an ocean as well as land. If the ocean is interactive and is being forced by the atmosphere, is moving, it's moving heat up and down and horizontally and so on, and evaporating and supplying moisture, then obviously it's a coupled model. And in a forced ocean model, sea surface temperatures are prescribed. They may change every day, every month, every season, depending on what is being simulated. And typically you look for things like whether the ITCZ is working properly in the model given the boundary conditions at the bottom, whether the monsoon is being done, so you may be looking at various processes, and there are some processes which are coupled and cannot be done with atmosphere only model, like an El Nino, even though now there is a bit of a debate about whether every El Nino is really coupled ocean atmosphere process or if there is just a thermodynamic coupling and so on. Having just the atmosphere model with prescribed boundary conditions allows long simulations, multiple simulations, because it's much cheaper to run just the atmosphere than a coupled model. As we said, adding carbon cycle to the coupled model will make it much more expensive, but even just the coupled ocean atmosphere model is much more expensive than just running an atmosphere model. So lots of process studies get done with the atmosphere only. And in terms of climate change, obviously atmosphere has very low heat capacity, doesn't have much of a memory. All of the memory actually just comes from the ocean, which means long-term trends, anthropogenic response, etc., are determined by the ocean and its ability to take up heat and store it away and release it on very low time scales. So the lower frequency variability depends on the ocean atmosphere coupling, whereas most of the weather time scales, ocean can be assumed to be a constant, which is how most weather predictions are done. But even climate processes are studied by atmospheric models by prescribing sea surface temperatures in various ways, by just prescribing the anomaly pattern of an El Nino, for example, to see how the teleconnected monsoon response occurs, or the Northeast Brazil response occurs, African response or high latitude responses, not only for El Nino but also to other ocean temperature patterns, for example. Okay, so let's leave it there. Atmospheric model is obviously a critical component of the Earth's climate system and Earth system. Given the top of the atmosphere radiation forcing, the models produce incredible number of features, basically all observed features, like the monsoon, trade winds, westerlies, ITCZ, their movement, El Nino, especially when it's a coupled model, and so on. But there are usually some deficits and biases and so on, which we will not discuss much right now. Okay. Actually, it's not a good idea to talk about atmospheric modeling and not mention the problem of clouds. In the sense, modeling clouds from basic principles is not easy, even though now there are models called cloud resolving models, which have high enough resolution that they can represent the scales of the processes of water parcels or particles interacting with, let's say, cloud condensation nuclei, forming clouds, and then other processes of collisions growing the clouds, and so on and so forth. But generally, modeling clouds is a very tricky and difficult issue, and there are usually also producing rain out of those processes. So you have convective processes which are not explicitly represented often, so there are convective parameterizations which take certain large scale parameters like statics, like, let's say, moist static instability in the atmosphere, and then look at moisture loading and do various other approximations of how the convective plumes adjust with the larger scale background and so on, and do cloud modeling and then precipitation out of them, how to trigger precipitation, and all those things are very detailed processes that are parameterized, so not solved by equations but statistically represented based on data from the field. And often there is issues of the processes coming from data on the ocean versus data on land. For a large continent like US, let's say, processes of convection and rainfall over Miami can be very tropical with elevated convection, rising air, condensing, producing convective clouds above, and so on. Whereas in the middle of the continent, you might have surface-based convection, which are happening by different processes than these. And there are, of course, times when air has to be pushed over the mountains, so rising air can expand, form clouds and rain, so-called orographic rain. So in general, models are very good at doing temperatures, but they have great difficulties in doing clouds and convection and rainfall. So this obviously becomes an issue in the global warming, as well as temperatures warm, atmosphere can hold more moisture, the Clausius-Clapeyron relation you remember, and then how much of that increased water vapor actually converts into increased precipitation is not completely understood, but a lot of studies have looked at observations to explain what is happening. And of course there are increases in extreme events. You can think of it as atmosphere warming as a sponge which is soaking up water, and rainfall process as something like pushing on the sponge that is now soaked with water. So the sponge is not going to drizzle everywhere, it's going to pour somewhere. So when you load up the atmosphere with moisture, extreme events increase, and even though the total rainfall, let's say, only increases by smaller percentage, extreme events can increase by a much larger percent, and the percentages depend on where you are, ocean or land, and so on and so forth. So cloud processes are very tricky, very difficult, and we don't know what is the net feedback of the clouds under climate change as well, in the sense, are they going to increase decrease in number and increase the albedo and lose more energy to space and cool and act as a negative feedback, or are they somehow going to become more absorbing, reduce the albedo, and have a positive feedback to global warming? These are not completely understood, even though satellite data has been used to infer some processes, and hopefully the models get better and data gets better and understanding gets better, so that we can know for sure whether clouds will be a net positive feedback or negative feedback. But in a model that can actually capture everything, these are what would be called emergent answers, so emergent solutions. Models may be able to say at some point in the future whether clouds will become net negative or net positive, but for now clouds are a big uncertainty in the models. Okay, so I'm going to leave it there for now.